All right, we're going to finish up our force vectors PowerPoint. This is part two. Hopefully you watched part one already. And so this is just going to be another walkthrough of a problem and just kind of give you an example of how this addition of vectors works. So we are looking at this situation. We have two different forces acting on this I hook. And what we want to do is figure out how much force is actually pulling on this, and then also what direction is it pulling. So we're looking for the resultant vector, the resultant force that you get when you put these two forces acting onto this hook. And so we have vector C, which is putting 300 pounds and is pulling upwards and to the right at a 60-degree angle from that positive x-axis. And it is pulling more vertically than it is horizontally. So when you start thinking about what kind of forces we're going to get here, this one's going to have more of an upward pull than it does a horizontal, but it's going to do both. It's going to pull to the right and up as it's pulling on there. So we know that we're expecting some of our force to go that direction. And then we have the second force, D, that is pushing downwards and to the right. So our overall force we know should be going to the right because both of the forces we have acting are going right. But what we don't necessarily know yet, because this force D is a little bit higher, is whether our resultant force is going to be up or down. And we know it's going to be kind of conflicting. C and D are going in opposite directions as far as the Y component. So we know that some of the force is going up, some of it's going down. So we need to kind of figure out where does that resultant force end up? Is it above or below? Is it up or down? And so we're going to start this the same way we did on that previous video by finding the x and y components of each of these two vectors. So we're going to look at C first and find its x and y components, and then we'll do the same thing for D. And then we're going to go ahead and add together the x components, add together the y components to see what the overall resultant force is on this hook. All right, so we'll start with C. And so for vector C, we do have 300 pounds. We talked about this in the last video that you, in theory, would want to draw this all to scale to where the length of that represents 300 pounds. And then you'd also draw the other one to scale so that, 300-pound force would be shorter than the 400-pound force. We're not going to worry too much about that. We just want to, again, get to the algebra of it. But if you were trying to do this geometrically, you'd want to take the time to make sure you scaled everything appropriately. What we are going to do is we're going to represent our force as the hypotenuse of this right triangle, and we're going to draw on the other two legs. One of those is the x component of our force C, and one is the y. And again, we just want to pay attention to the sides. And so this one's set up typically like we're used to, so that the opposite side is y, the adjacent side is x. So we're going to start off by finding x. And to do that, because it is the adjacent side, we know we're using cosine. And so the way we find that value is we do the force C times cosine of the angle. So it's 300 pounds times cosine of 60, and it's going to the right, which we said earlier. And so we'll put that in our calculator. 300 times cosine 60 gives us a total of 150. And cosine of 60 is a half if you are interested. You can kind of see that that's what happens. So we have 150 pounds pushing to the right, and then FCY should be greater than that because we are at an angle greater than 45. And so we're going to do 300 times sine of 60 because FCY is the opposite side. And so for opposite, we use sine. And so we do 300 times sine of 60, and we get 260 pounds. Again, these are rounded. It's not going to be exactly 260 in this case because sine of 60 is not going to come out to a perfect number like half. But we're going to round it off to, it's pretty close to 260. So those are our x and y components for this vector. So we know 150 pounds are going horizontally, 260 pounds are going vertically, and that is kind of the resultant forces of this, and the component forces of this vector C. All right, so we're going to do the same thing for D. So we'll go down and look at D. Now this one is going at a different angle, and it is going down and to the right. So we're going to draw it this way, which is the correct way. But we do have to remember when we look at our forces, if it's going to the right in the x, it's positive. If it's going down, it's negative. And if it's going up, it's positive. So in this case, y is going to be a negative value. So we're going to calculate it like we would in geometry and just find the value. But we're going to have to remember to make that value negative. We can't just leave it the positive value, even though the actual length would be a positive value, but we're looking at the direction, and the direction is down, so that makes it negative. All right, so let's take a look and look at x first. And again, x is the side adjacent, so it's next to my angle, so that side is going to be the one that uses cosine. And so we're going to get our force times cosine of 30, and we'll plug that in. And of course, this is going to be something we do on the calculator, and so you're going to get 350 pounds. Again, it's not going to be exactly 350, but it's approximately 350. We're rounding. We talked about this before with Project Lead the Way stuff, that they tend to round to significant figures. And so that's what's happening here. So if you do it on your calculator, you're not going to get 350, but you'll get something close to that. All right, and then we want to do y. So y, again, is opposite sides. So we're going to use sine. And so we get 400 times sine of our angle. So it's times sine of 30. And sine of 30 turns out to be a half. So it's 200. And then we make it negative because it was down. So this negative is not going to show up on your calculator. If you just put 400 times sine of 30 in your calculator, you're not going to get a negative value. You're going to get 200. What we have to remember is because it's down, that is where that negative is coming from, because we're putting that direction onto it. So don't forget it. That is the biggest mistake people make between that and just switching up the sine and cosine. But as far as getting the signs correct, that's the big thing with that. If it's down, it's negative. All right, so we found the x and y components for the c vector, found the x and y components for the d vector. So now what we want to do is add together our components. So here we're going to draw in, here's the x and y components we had for c and for d. So we're going to add together our x components, and we're going to add together our y components and get the resultant x and y components. So what is the overall force acting in the x, overall force acting in the y for these combined things? So we're going to add these two together. We're going to add these two together. And so let's go take a look and see what we get when we do that. So if we sum our forces in the x direction first, we're going to get just these two added together, FCX plus FDX. And they're both positive, so they're going to add up and get a larger value. So we're going to kind of figure that would be the case since both of them are pushing in the same direction. And so our value ends up being 496.4. So we're just a little under 500 pounds to the right. And that is our x component. So 496.4, that is the x component. And because it was positive, we know it's still going to the right. When we add our y values together, here one of them is positive, one's negative. So we are going to add them, but when you add a negative, it's basically subtraction. So we're going to basically be subtracting these. And so we get 259.8 minus 200, because we're adding that negative. And so we end up with 59.8. So now this is where I have to really pay attention. Since one's positive, one's negative, it will determine the direction by the sign. So since it ended up positive, we know it's up. If it had been negative, we know it was below the x-axis. It would have been going a downward direction. But in this case, it's positive, so we know it's going up. Now it is quite a bit smaller because we did have competing or conflicting, going opposite directions with our forces. So it is quite a bit smaller than our x. And so we should expect then that our angle is not going to be real steep. We have a lot of x and a very small y. So if we start looking at what that triangle is going to look like, it's going to be a very long but not very tall triangle. And again, since it's right up, we're not going to worry too much about that. I mean, it's something you should be thinking about, but we don't have to worry about that terminology necessarily. All right, so let's look at how we finish this off then. So now that we know what those two components are, on that last problem we had in the previous video, the y was 0, so we were pretty much done at that point. But here we have a little bit more work to do because we want to look at what is the overall force going to be. So we have the two components. We want to figure out what the hypotenuse of that resultant force is and what angle is it going at. So we want to figure out those two things. So we're going to start by just looking at, well, how would we draw that out? The resultant vector force would look basically like this. We have our x component, we have our y component. And so what we're looking for then is that hypotenuse. Now they're going to show you an alternative way to draw this, which is really the same thing if you want to do it with the y first and then the x. It doesn't really change the fact that we're getting the same vector, same blue resultant vector. Either way you draw it is fine. And you just kind of usually choose whichever fits your picture best. So, if you have something already there and you need to go one versus the other just for space sense, that's fine. It doesn't really matter. They're going to be the same. And so what we're looking for is f of r. And of course, this is easy. If you remember, what is our method for finding the length of a hypotenuse of a right triangle? Well, we're going to use Pythagorean theorem, and we know the two side lengths, so we just need to find the hypotenuse using Pythagorean theorem. So that's what we're going to do. So we're going to do 496.4 squared plus 59.8 squared, add those together, and then that is what c squared, that's my hypotenuse squared. We'll take the square root of that to get our length of our hypotenuse. So we'll kind of walk through that real quick. And so you get our squared, add them together, take the square root. And so we're coming up with about 500 pounds. Again, this is probably not exactly 500, but it's really close. If it's not exactly, it's going to be really close. So we got about 500 pounds of force. That is our resultant force. That is the net force acting on this with those two other forces. So those two forces are going to combine together to give us basically 500 pounds of force acting on that hook. The other thing we want to know is, what is this angle? What angle is it pulling at? Because it's not going to be pulling at the same angle as the two cords we have on there. It's going to be pulling it somewhere, we would assume somewhere between the two. And so that's what we're going to look at, is where is that going to end up? So we know the magnitude. Let's find that angle. And so to find the angle, now that we know the hypotenuse, we really could use any of the trig functions, but we're going to go ahead and use tangent just because the two things we knew were the two sides. So we're going to go ahead and use tangent to do this. But realistically, once you know the hypotenuse as well, you could really use sine, cosine, or tangent to do this step. But we're going to use tangent. So we know tangent of the angle is equal to the opposite over the hypotenuse. And so we're going to get this ratio. And to solve for the angle, we know the tangent of the angle equals this ratio. We need to undo that tangent operation. And so it's not an algebraic operation. We're not multiplying, dividing, adding, subtracting. And so we don't really have a good algebraic way to solve this. So we are going to just have to go to the calculator, and we're going to find the inverse tangent. Inverse tangent is the opposite operation. It undoes tangent. And so we're going to find out that the angle is the inverse tangent, the opposite operation of that tangent of that ratio. So we're just doing inverse tangent of both sides of that equation to solve for our angle. And so you put that in your calculator. Just again, make sure you're in degree mode for all of this stuff. If you're not, we're going to have some problems. But we'll plug that in, get a value. In this case, it comes out to about 7 degrees. And so that means that we have a 500-pound force acting at a 7-degree angle counterclockwise from the x-axis. So it's just a little bit above the x-axis, about 7 degrees above. And that's the resultant force. So that's kind of what we were looking for. We're going to be looking at some of those same things when we start doing the bridge trusses. Primarily, we're more interested in the force than we are so much the angle, but finding the angle is often a thing that you're going to want to know. So that is something that you would want to know how to do. All right, so that is the review. Again, we did this back in the fall, so that's a quick review of how to do the force vectors. We're going to start looking at kind of the whole process that you need to go through to do the bridge trusses after this. So be looking for an assignment on these force vectors. There's a quick review assignment for those, and then we'll get into the actual bridge trusses and kind of the build up to that.